DynamoDB is a fast, scalable, and highly available distributed key-value storage system that was built at Amazon to provide an always-on experience to its customers. To achieve this level of availability and performance, Dynamo made some design decisions that trade off consistency and kept its interface extremely simple. A user can perform only two operations, get and put. A get operation fetches data from the system based on the key, and a put operation either initializes or updates the value for the given key. So there are no complex queries or operations on multiple data items like in relational databases. Dynamo made another decision that differentiated itself from the relational pattern. While transactions in relational databases are ACID, Dynamo sacrifices the consistency part of it to be faster and more available. In this video, we're going to focus on the two main design decisions that helped Dynamo achieve this scalability, speed, and high availability. The first one is how Dynamo partitions its data across the machines in the cluster. Dynamo uses an improved version of consistent hashing to distribute the load so that it can incrementally scale by adding more machines to the cluster. Consistent hashing is a technique that helps efficiently partition data over a large cluster of machines. When data needs to be distributed, one simple way to do that is to hash the data and store it on a machine based on the key that's associated with the hash. This works well when there is a static amount of machines in the cluster, but in a large cluster, the number of available machines frequently changes because machines fail or new machines need to be added to the cluster to address the resource needs of the system as it scales. With this technique, each time the number of machines change, we need to shuffle around the data because the data hash key to machine mapping keeps changing. In a large cluster, it will become impossible to have the system be performant, but it always needs to keep using its resources to change how its state is saved. To address this, with consistent hashing, all the possible keys, which are also called the hash space, are represented as a ring so that the first key is followed by the last key in the hash space. We hash not just the data, but also the machines in the cluster and place them on the ring. Each time we have a key of a data item that we need to decide on which machine to store it on, we will simply choose the machine with the closest, larger key to the key of the data item. Now, if we want to scale and add a machine to the cluster, we will need to shuffle only the data items that will need to go on that new machine. There is a limitation with this basic consistent hashing technique. The hashing function can result in keys that place multiple nodes close to each other on the ring such that the data will not be distributed evenly. To address this, Dynamo uses a variant of consistent hashing. Instead of mapping the hash of a node to a single key on the ring, each node has a list of keys that go on the ring. Each of those keys is referred to as a virtual node. Dynamo maintains the mappings of real nodes to its virtual nodes, and by using a large number of virtual nodes for each real node, it improves the uniformness of the distribution across the cluster. This way, the system becomes horizontally scalable and efficient. Add more machines and you have more resources to handle the larger scale without needing to shuffle around lots of data. The first thing that Dynamo does to achieve high availability is to replicate each data item that has some key k across n nodes, starting from the first one that the key would map to, and this is called the preference list. Since Dynamo uses virtual nodes, when replicating data items, the different virtual nodes that map to the same real node in the preference list will be skipped so that only n distinct real nodes will be in the preference list of each key. But the important decision that Dynamo makes to be truly always on and performant is to make the put operation asynchronous. So the put operation call can return to the caller before all the replicas are updated, and a subsequent get call operation may not return the most up-to-date object. When there are no failures, the propagation time of the update is bounded. But with server outages or network partitions, it will take longer for the system to become consistent. Before we continue, for example, one of the applications that can tolerate this delayed eventual consistency is the shopping cart application. We want it to always be available because we want to make sure that when a user adds an item to the cart, it is never forgotten or rejected. If there is a network partition, a server outage, or some other failure that prevents the client from interacting with the same server, that has the most up-to-date shopping cart, instead of having the cart unavailable until the system is consistent and all replicas store the same state, we would let the user keep making updates to older versions of the cart so long we have the divergent versions reconcile later on. To provide this kind of a guarantee, Dynamo treats the result of each modification as a new and immutable version of the data and allows for multiple versions of an object to be present in the system at the same time. Most of the time, when new versions of an object are available, the older version will be garbage collected. But when there is a network partition and concurrent requests are made, there could be diverging versions and it becomes harder to tell how they should be reconciled to form the newest version of the object. To address this, Dynamo uses vector clocks for each object version. Vector clocks are used to capture causality between different versions of the same object to assess which one is the older version and which one is the newer one when there are multiple versions at the same time. A vector clock is a list of node and counter pairs. Each pair has a key that identifies a node in the cluster and a counter. So for each value in the system, we don't only have a key associated with it, but also the context, which is its vector clock that determines its version. Whenever the client calls the put operation, it needs to specify, in addition to the key of the object and the desired value, the version of the object it is updating. That version is the context we are passing, which is the vector clock that we receive on a previous get operation. Let's see how this works. First, the client writes a new object, like creating a new shopping cart, for example. The node that handles that request, say node A, creates the first version by initializing the vector clock of the object to a pair of node A and 1 as the sequence number of the counter. The client makes another write request, say we add an item to the shopping cart. Node A handles that request as well and creates a new version of the object by incrementing the sequence number by 1. Node A now has 2 versions, and thanks to the vector clock, it knows that the version with 2 as the sequence number is the up-to-date one because the pair with sequence number 1 is reflected in it. So the first one can be deleted. The older version may still linger in the replicas until the update propagates to those nodes as well. Now we have a network partition. There is some failure that causes node A to not be able to handle the next request. Next time we add an item to the cart, node B handles the request and creates a new version. Now the vector clock for the new version will have 2 pairs, one with node A and sequence number of 2, and another one with node B and sequence number of 1. The older version is reflected in the new vector clock, so node B knows it can delete it. Let's assume now that we read the cart with another client and then try to update it. Node C for this client reads the newest version that was propagated from node A, as the changes from node B haven't propagated yet, so we end up updating not the most up-to-date version, and the new vector clock for the object node C creates is a pair with node A and sequence number 2 and a pair with node C and sequence number 1. It also knows that it can delete the version that was propagated from node A because it is reflected in the new vector clock that it just created. At this point, we have diverging versions of the shopping cart. The updates in node B are not reflected in node C and vice versa based on their vector clocks, so we can't automatically reconcile. In this case, both versions of the object have to be persisted and presented to the client in their next read operation so they can determine the desired state of their shopping cart. Once the client reads again the shopping cart and performs the reconciliation, assuming that node A is back and healthy, it handles the request. Node A will merge the vector clocks and then update it to represent the new reconciled version. In this case, the sequence number for node A's pair will be incremented to 3, and the other replicas will be able to automatically reconcile all other versions since now they are all reflected in this new one. If, say, node D instead handled the read request when the client reconciled, then the vector node will have a 4th pair, and in this case also there will be no longer diverging versions and other replicas will be able to reconcile on their own because the other versions are all reflected in this current one. One limitation with this design is if there are many concurrent requests and many network partitions, there could be many diverging branches, and the size of the vector clocks could indefinitely grow. Amazon decided to address this by simply using a threshold, say 10, to the amount of pairs in the vector clocks. Once that threshold is reached, the oldest pair is removed. This can lead to inaccuracies in some cases when reconciliation is necessary, but it is unlikely, and Amazon also made a note that this problem hasn't actually surfaced in production. So with a variation of consistent hashing and asynchronous writes using vector clocks for versioning, Dynamo can scale and provide an always-on experience to the applications that use it, and can tolerate the trade-off it makes to be virtually always available. If you want a Notion cheat sheet for Dynamo and other free resources, you can check out the link below. And with that said, thank you for watching.